So, stochastic calculus 1. But it will be only the first shot, okay, because I have not the possibility to do it. Okay, so who are you? Noor? Dalia? Dalia. So my email, I have an email from Paris 1, okay, but I have also a Gmail address, okay, you can use both. So I won't use the light of the board because, okay, if I use it, okay, for the camera it's not good. So you have my, so Christophe.Choro, okay, at Gmail. You have my website, that is the same thing. You have a teaching, so you have a link with toward another site here, okay, whatever, and in this other site you have a teaching session, okay, you find the course, stochastic calculus, and in particular you have here, okay, what you need, in particular, the lecture notes, okay, that are in English or in French. Okay. So a priori, I will do the course in French. Okay. Except if everybody speaks French. No. No. One here. You don't know. Oh. I will do it in English. Okay. So typically, okay, if you are not able to do live session, okay, it will be a precious tool for you. Okay, you have all the course that is like a book, okay, and that is self-contained. So you will have a final exam, simply, no midterm exam, okay, just a final exam. That is in February. But this course is a little bit complicated, okay? So if you wait for January in order to study, because for the first semester I will study the other topics, okay? It's a very, very bad idea, okay? So you have to work regularly, okay? So we have courses, and included in the course we have exercise sessions, but I will do them both at the same time, okay? I will do some exercise from my lecture notes, okay? During the course, exactly as we are going to do today. If you want a picture of me without the mask, you can Google me, okay? Unfortunately, I think that this here, okay, you will see me with the mask only. So just a remark concerning the lecture, okay? So the course is called Stochastic Calculus for Finance, okay? So we are going to do finance, okay, but not now. Okay, we are going to start with stochastic calculus. And in particular, I will do big reminder concerning probability theory. It's what I call in the lectures note, okay, the chapter 0. And for this chapter 0, it will take me, okay, more or less 1 month to do it. Okay, so it's a reminder, but a big one. Okay. I won't start it today from the beginning, okay? I will drop some very bad things, okay? And if you have some problem with them, okay, come back to the lectures note, okay, and send me some question if you want, okay, after the session. I will start with the notion of Gaussian vector today, okay? And after we will do conditional expectation. We will study stochastic process in general, okay? It's more or less what we are going to do in the chapter 0 with Martin Boltz also, okay? And then chapter 1, Brownian motion. Chapter 2, stochastic integral. Chapter 3, 2 mathematical results that are important for the finance, that are the Gaussian theorem and the martingale representation theorem. Okay, and then we will do the part concerning finance. Okay, so Stochastic calculus is really the main part of this course, okay? But I will try to apply it, okay, to the very beginning of mathematical finance, and I will do, okay, in all the details, okay, the Black-Scholes model and some extensions, okay, but really in details, with all the mathematical details. Okay? I know that some of you have already seen this model a little, okay? Now we are going to do everything, okay, and it will take us 4 months, okay, in order to have all the maths related to this model, okay? So of course, I know that for some of you, this course is an option, okay, but if you want to do, typically in the second semester, courses dealing with quantitative finance, you have to take it, okay? Because you will need stochastic calculus. My office. So for the office, okay, you know, it's a little bit complicated now, okay, with the COVID and so on. So I am in my office, okay, 413 small a, okay, on the 4th floor. I have a lot of courses during the first semester, so if you want to see me, it's better to send me an email to have an appointment, okay, it would be better for everybody, okay. Do you have some questions? So it's a big course, we have 36 hours of course, and I don't know, around 16 or 18 of exercise that I will combine, okay, into something of 54 hours, so it's a big part for you for the first semester. And you know that this course counts twice with respect to the smaller one, okay? Okay. So let's go. So you have received an email from Miss Nago concerning the fact that the lecture notes are available. For some of you, you have received it, okay, at the beginning of June, something like this, no? I remind. So I won't be able to print them this year. Okay, so you may use, okay, this, an iPad, okay, or computer if you want, but I think that if you want to put and to give some notation on the paper, okay, it's better to print them. Because, okay, typically for some very big definitions, since this year I have a very, very small board, okay, in order to do mathematics, okay, I won't copy everything, okay, on the board. I will try to be as precise as possible, okay, but typically for very big propositions, okay, you have lectures notes, we are going to use them, and I will do the proofs on the board, okay? So no questions? So a priori I have here only IRFA students, or I have MMMEF students? So one student?
Yeah.
Okay. So, since we have only one student, so just a few words concerning this. So, a priori, this course is also open, okay, for some very particular MMEF student, okay? At the beginning, so we will discuss at the end maybe, okay, to see if it's possible for you or not, okay? Typically because I have a small room, and of course it's a course from the IRFA track, okay, so IRFA students, but if we are in this situation, a priori no problem for me, okay? But we have to discuss, okay, and I have to give you my okay, and also Miss Nago, okay, and also I have also to discuss with this point, okay, for with Olivier beyond the end of the MMEF program. Okay? So you have everything here. Okay? You can find other things here, okay, a course of probability, so some other documents, okay, that are available. Okay? So a priori, I hope that we will be able to do class, okay, every Tuesday, okay, of the semester. If it's not the case, I don't know how we will do. Maybe 2 groups, okay, of students, okay, 1 week to another one. I don't know. If we do this, okay, I will use my computer in order to do videos of the course. So with videos, lectures not, okay, maybe some Zoom session in order to answer questions if you have. I think that it will be not that bad, okay? And if everybody is at home, okay, I will do my course from my home in Marseille, okay? So you will see the sea, okay? We'll do it. It's possible, I will. Okay, so let's start, okay, with the chapter 0 of the course. That is a big reminder concerning probability theory. Okay, so very big one that I will start today and maybe finish at the end of September or the beginning of October. Okay? So no questions? So if you forget the link of my website, okay, you write my name in Google, okay, and you find it, okay, immediately. Okay, so where are my notes, okay? Here. So I will start today, okay, not with the very beginning, okay, because I come back to the definition of what is a random variable, what is a probability, and so on, okay? But I will start with something that will be very important for us in the chapter 1, that is the notion of Gaussian vector. Okay? And what is the notion of Gaussian vector? Okay, some of you already know this notion. Okay? It is just the extension in a dimension higher than 1, okay, of the notion of Gaussian random variable. Simply. Okay? So Gaussian vector. So but I think that it's a good idea for you, okay, to read the beginning of the notes, okay, it's not that long, okay, but to read them, okay, already the case. Okay, so let's start. I consider, okay, the random variable. So to define the random variable and its distribution, okay, I need first what we call the probability space. Okay. Probability space. What is a probability space? It's just a set called the universe. You have here the sigma algebra. Okay. And here you have a probability. And I remind you that the probability is what? The probability is just a mapping P from the sigma algebra calligraphic A into the interval 0, 1. That fulfills, in fact, two conditions. The probability of the universe is 1. Okay? And I have the sigma additivity property, that is, if I have a sequence of pairwise addition sets, the probability of the union is equal to the sum of the probability. Okay, so I don't write the definition of a probability. You have it at the beginning of the lecture notes. Okay, and my sigma algebra here, on which is defined my probability, is the second element of my triple. Okay, so I have this. So let's consider a random variable that is a real random variable defined on this space. Okay, so what is the meaning of the random variable defined in this space? So I have a mapping that is from omega, the set, okay, I call W its argument, okay, with values in, let's say, R here, okay, and give x of W, random variable. And what is a random variable? A random variable, okay, is just a mapping, but that is compatible, in fact, with the structure I have here, typically the fact that I have a sigma algebra. Okay? So do you remind the definition of a random variable? For x to be a random variable, what I need to check? You remember this? So here I have the real numbers. I know that I have a natural sigma algebra on the real numbers, that is the Borel sigma algebra. Okay? And so be a random variable here means that for any b belonging to the Borel sigma algebra, then the preimage of b by x belongs to A. This is the definition of being a random variable. The preimage of any Borelian belongs to the sigma algebra that equipped calligraphically. Okay? So when we do probability, okay, we work with mapping that fulfill this property. Why? But because we have a probability on this set here, defined on this sigma algebra. If I suppose this regularity condition for capital X, I will be able to define a new probability that is defined on the real numbers, and more precisely, on the Borel sigma algebra. It's what I call the distribution of capital X. Okay? So what is the distribution of X? Okay? It's a new probability, so I have a probability here, P. I am able to transport here from omega to R through capital X, okay? And what is my definition? So I am defined on the Borel sigma algebra, of course with value in 0, 1, and to any Borelian, the value is this one, P of X minus 1 over P. And you see by this definition how and why you need this. Because P, the probability, the initial probability, is defined on calligraphic A. If I want this one to be well defined, I need this one in calligraphic A, and it's exactly what I have if I suppose that X is a random variable. So the notion of random variable, okay, is the good notion if I want to transport probabilities. And this P of X here, it's what we call, P of X is what we call the distribution of X. So, in a classical course of probability, okay, you have several classical examples of distributions. You have the Poisson distribution, the uniform distribution, and so on. Okay, you have plenty of such particular distributions. What we are going to do today mainly is to speak about Gaussian. Okay, so X is from omega into R. We say that X is Gaussian. So what is the definition of being Gaussian?
Mean of mu and the sigma square, the variance.
So more precisely.
0. No, it's not. So it's Gaussian.
Normal.
Yeah, but what is the definition of being normal?
Sigma.
So I can define it through the fact that capital X has a density function. Okay, so equivalently, okay, I can write it this way. I can use the density function. Ask me. Okay, question? No? Okay. So density, okay, what is the density of a Gaussian random variable? Okay, you have the classical formula that is 1 over the square root of 2 pi sigma square exponential minus x minus m square over 2 sigma square, okay? And it's easy to see that I have two parameters here, two real numbers, okay? M that is in fact the expectation, the mean of capital X, and sigma square that is its variance here, okay? So a Gaussian random variable in dimension 1, okay, may be characterized by its density function. Okay? Another way to characterize capital X. So, the moment generating function, but in this course, okay, I won't use the moment generating function. I will use the characteristic function. That is just the complex counterpart of the moment generating function. So, the characteristic function So what is the definition of the characteristic function? So in grid generality, it's what we call phi of capital X at the point t, let's say, okay, where t is a real number. It's just the expectation of exponential I t capital X. And in particular, if you take t equal to minus I small x, you recover the moment generating function here. Okay? So I have this, the characteristic function, I is the complex number I, such that I squared is equal to minus 1. Okay? T times x, t being a real number here. And what is the value of this characteristic function for a Gaussian random variable? So it's something that you have to know, and something that we are going to use, okay, 1,000 times in this course. Okay? Really 1,000 times. So what is this? So if you have to know one characteristic function, it's the one you have to know. So what is it? Nobody knows? No? Exponential I t m, okay, minus sigma squared t squared over 2. So this is the characteristic function of a Gaussian random variable. And as suggested by the name, okay, the characteristic function characterizes the distribution. So if you have a random variable and you prove that its characteristic function is this one, you are sure that it is a Gaussian random variable with parameter m and sigma square here. Okay? So it's something that characterizes the distribution. So if I want you to prove that you have something that is Gaussian, you can try to compute its density or try to compute its characteristic function. If you find this one, it's a Gaussian. Okay? So it is what happened in dimension 1. Okay? So what we are going to see here is to extend the definition of a Gaussian random variable to the case where capital X is not something with values in R, okay, but something with values in R to the power of someone, to the power t. Okay, so we are going to work with random vectors instead of a single with random variable. Okay? So we are going to take this definition and after I will comment, okay? So I will use exactly the same notation in the one in my course, okay? So I have written lectures note, okay, it's to use them, okay? So it's the definition 0.7.1, okay? So it means that I am in the chapter 0, it's the section 3 of the chapter 0 here, okay, in the first definition, okay? So now I consider a capital X is not a single random variable, okay, but a vector. So let capital X equal to x1, xn be a random vector. So what I mean by a random vector, okay, a random vector is just something, okay, a vector with each component that is a real random variable. Okay, so you have something with values in R to the power n here, okay, x1 is a real random variable, x2 is a real random variable, until xn, okay. And we say that capital X is a Gaussian vector if what? So you have not the sum, we are not very far, but it's not the sum, or linear combination, okay? So in particular the sum, okay, but all the weighted sum if you want, okay? So I will write it in the short way. So if for all x belonging to R to the power n. So I consider n real numbers, okay? Then the scalar product between small x and capital X is the real Gaussian random variable. So what is the scalar product? Here it's the classical scalar product in R to the power n. That is simply the sum from I equal to 1 to n of small xi, the i's component of this vector, okay? Capital X. I have this, okay? So if I want to give you a definition in English, a random vector is a Gaussian vector if and only if, okay, any linear combination of its components is a real Gaussian random variable. Okay? So it's the definition of a Gaussian vector. So some remark concerning this definition. And before to do this remark, okay, just remind the convention I will use, okay, when I will speak about vectors. So in this course, okay, vectors, so x belongs to R to the power n, okay, will be written. So you know that when I deal with vectors, okay, I have two possible conventions, to use line or to use column. Okay? In this course, I will use the column. Okay? So you know that it's something that is important because, okay, if I want to do matricial products, okay, it's something that we'll use. Okay? So typically, do you have a way to write this one, okay, just using products of vectors? This one. So I have the vector small x, okay, the vector capital X. If I want to write this sum here, using these vectors, and this one, okay, that I will write, okay, from now on as a column, okay, not a line here. X transpose capital X. What I do, so X transpose capital X is what? I consider the line and I multiply it by the column, and if I do the matricial product, I have exactly the sum of the xi, capital Xi. Okay? And you have here a matrix of size 1 n, here a matrix of size n1. That's why at the end you obtain a number, okay, something of size 1, 1, okay, a number. That is the sum of the xi, capital X. Okay, so another way to write this scalar product, okay, is just X transpose capital X. Okay, where X is the transpose, something that changed the lines into columns. Okay. So remark concerning my definition here. If I have a look on this definition, I can say the following. If I have a Gaussian vector, what can you say about its components? They are all Gaussian. Why? Well, I can take small x equal to 1, 0, 0, 0, okay, do the sum here, and I obtain x1. If I do the same for 0, 1, 0, 0, 0, I obtain x2, okay? So doing particular choice for small x, okay, the vector of the canonical basis of R to the power n, I obtain that if x is Gaussian for all I belonging to 1 n, the xi then is, let's say, the Gaussian vector here. For all I belonging to 1 n, xi is the Gaussian real random variable. Okay? So if I am a Gaussian vector, my components are Gaussian random variable. But be careful, because the converse is false in general. Why I have this? Why the converse is false in general? Because, okay, what is the converse? If all the xi are Gaussian, x is a Gaussian vector. No. Because the definition, okay, is more restrictive. All linear combination of the components are Gaussian random variables, okay? Not only the components of my vector, okay? So maybe in exercise we will see an example where, okay, you have something where the components are Gaussian random variable, but you don't have a Gaussian vector. It's possible to build this, okay, easily. So when I am a Gaussian vector, my components are Gaussian, the converse is false in general. But do you have a simple situation in mind where the reciprocal is okay in fact? Hmm? Yeah. So in the situation where we suppose an extra condition here, I suppose first that they are Gaussian, and if I suppose that they are independent, then I have a Gaussian vector. If the xi are Gaussian and independent, x is a Gaussian vector. So here it's an easy situation where you have a Gaussian vector, okay? If you have the independence of the component and the fact that the components are Gaussian, you have a Gaussian vector, okay? But it's not the only situation. You have situation where you have a Gaussian vector, but where the components are not independent, okay? So we are in particular situation. So why I have this? Well, from a result you know about real Gaussian random variable, the fact that if I have two Gaussian random variables that are independent, okay, if I take a linear combination, it is still a Gaussian random variable. But if they are independent, okay, if they are independent, okay. So to continue. At the beginning, I have said that if I have a real Gaussian random variable, I can characterize its distribution by two parameters, the mean and the variance, the small m and the sigma square in the definition of the density or in the definition of the characteristic function. Here, in the case of Gaussian vectors, we are going to prove the same kind of result. In fact, if I have a Gaussian vector, okay, its distribution may be characterized by two parameters that are no more real numbers, but a vector and a matrix. A vector that will be the mean vector, the vector of the mean, okay, and a matrix that is the variance covariance matrix. Okay? So we'll write it here. So it's a proposition, a little proposition. Okay. 0.3.1. So if capital X is a Gaussian vector of R equal N, so it's not really possible for me to write bigger because I have a small board, and if I write bigger I will erase every time, so I try to keep the definition, okay, as I came on the board, okay, so that's why it's important for you to print the lectures, not values. So if X is a Gaussian vector of R to the power N, okay, I said that I have explicitly its characteristic function. I have explicitly its characteristic function. So here I have a number or a vector of real numbers in R to the power N, okay? The characteristic function in this situation is the expectation of exponential I, the scalar product between X and capital X. So this is just the definition of the characteristic function, okay? Nothing to do with my proposition, it's a general definition. And what is this one, okay? So I have this formula, okay, that is simply exponential I X n, okay, and I will define just small m just after, okay, minus, okay, of this one, X transpose sigma X over 2, where m is the vector of expectations, so m is equal to expectation of x1 until expectation of xn, okay, and sigma is a matrix, that is the variance covariance matrix, that is a square matrix of size n, where I have inside the covariance between xi and xj, for I and j between 1 and n. Okay? So I can deduce from this proposition that a Gaussian vector may be characterized simply by two parameters, its vector of mean and the variance covariance matrix. Okay? So in particular, if I take small n equal to 1, I recover, okay, exponential I x times n, and here minus sigma square x square over 2 if I am a number and not a matrix here, not a vector. Okay, so for n equal to 1, I recover exactly, okay, what I have reminded at the beginning of the session. Okay, so I have this one.
Professor, I don't understand what's this I.
This I?
Yeah.
The same as before, the complex number I. Okay? The one that I square is equal to minus 1. Okay? The complex number I. So sometimes you call it not J, it's I. Okay. Purely imaginary number. Okay? Okay, so I have this proposition. Okay? So let's prove it. It's complicated for you to read here. I know, okay, but I will try to do my best. But the problem is that, okay, if I put a line here, I will have a board that is very small. So I keep the definition of the Gaussian vector here. I keep this proposition here, okay. And let's do the proof of this proposition. It's not that complicated, okay? This proof is just a consequence of the definition of the characteristic function of a Gaussian. Okay. So, in fact, I want to compute the characteristic function, okay, of something that deal with the scalar product between x and capital X. Okay. I remind you that the scalar product between x and capital X is simply the sum from I equal to 1 to n xi capital Xi. So if you have some question, okay, ask me. Huh? It's my job. I'm paid for this, so okay. I'm drawing. So what can you say about the distribution of this one here? What is this random variable? What is the distribution of this random variable here? I have an hypothesis in my proposition. Huh? Capital X is a Gaussian vector, meaning that a linear combination is a Gaussian random variable. So I know that this one is a Gaussian random variable. Okay? If I want to characterize its distribution, it means that I have only to know the two parameters here. Okay? That is the mean and the variance. Okay? So, here, for the mean, if I consider the expectation of small x capital X, what I obtain here? By linearity of the expectation, I obtain the sum of the small xi expectation of xi, that I can write using this notation here as x small m, where small m is the vector of the expectation. Okay? So using the linearity of the expectation, I obtain for the expectation of the scalar product between x and the vector of expectations. Okay? So if I want to obtain the second term, okay, what is the second term in the Gaussian?
The variance.
The variance. So it's the variance of the scalar product between small x and capital X. So here, unfortunately, you know that the variance, okay, is not linear, it's a quadratic form, okay? But I have a formula concerning the variance of a sum. I don't have independence for the xi, so the variance of the sum is not the sum of the variances, okay? But I have a general formula for the variance of the sum, and I obtain the double sum. It's the sum for I and j between 1 and n of what? X indexed by I, xj, the covariance between xi and xj. Okay? I use the fact that the covariance is a bilinear form, or equivalently the fact that the variance is a quadratic form. Okay? So the variance of the sum is given by this double sum here. Okay? And I will try to express it using this matrix here, the sigma. So here I have a double sum, xi, xj covariance. So I can express it, okay? It's just a little trick concerning linear algebra. I can write it as x transpose sigma x, where small x is the vector x1, x2, xn. Why I have this? Here I have a vector of size 1, n, here n, n, 1, so I obtain a number that is given by this one. Okay? So it's just a little trick about linear algebra. Okay, so it means that I know exactly the distribution of this one. Small x, capital X follows the n, m, x, x transpose, sigma x. Okay? Clear for everybody? So It's a question. What is the answer? You have the scalar product. If you inverse the coordinates, you obtain the same thing. So I will use the same notation as here, but it's exactly the same thing. Yeah? Okay? X and the scalar product is symmetric. Okay? By definition. Okay. So keep in mind what I want to do. So now I will erase the definition. I want to compute this, but I am able to compute it because I know the distribution of this one. So it's something, the computation of this one is something that is related to the computation of the characteristic function of a real Gaussian random variable. Okay? I continue my proof on the third part of the board. Okay? So I am interested in the computation of this expectation here. Okay? What I know is that if Z follows n, let's say m sigma square, okay, and to make confusion with this small m here, we have already seen that the characteristic function of Z at the point t is equal to exponential I t n minus sigma square t square over 2. It's the result for the Gaussian random variable. Okay? So what is the term I am interested in? The term I am interested in, okay? Keep in mind that here the definition is the expectation of exponential I t. So having this in mind, okay, I can say that phi of capital X at the point small x may be written using this Gaussian random variable here, and it's just phi of the Gaussian random variable small x scalar capital X, at which point I don't have the t here, it's just t equal to 1. Equal to 1. And now what I have to use is simply to use this one. What is my mean? My mean is given by this one. My variance is given by this one. So I have simply to apply this formula with capital M equal to x scalar M. Sigma square that is equal to x transpose sigma x. Okay? And take t equal to 1. And I obtain 1. I obtain exponential I x m minus by the sigma square that is x transpose sigma x over 2. And if you need the proof, because it's exactly what I want here. Exactly what I want. So when I have a Gaussian vector, it's very simple for me to recover its characteristic function that you have to know. Okay, and I deduce it in fact from the characteristic function of a real Gaussian random variable. Remarking that this one is Gaussian by definition of a Gaussian vector. I am able to know the mean and the variance of this one, and I plug inside the characteristic function of a real Gaussian random variable. Okay? So I have this. So real Gaussian random variables are characterized by their mean and their variances, okay? A Gaussian vector is characterized by its mean vector and the variance covariance matrix. Okay? Clear? So it's classical computation, nothing complicated, okay? It's the warm-up. Okay, I will start during the two first session by this kind of little computation, okay, in order to. Okay? So now we are going to handle a little the definition of Gaussian vector. Okay? Seeing, okay, some corollary and some exercises, okay? That will be important in the following. So tell me if I can erase the board, everything? Okay? So I erase everything. And let's see, okay, one corollary and two little exercises dealing with this proposition. So I have to erase carefully the board, okay, if I want that the video is okay. So. Okay, a little corollary. That underline the interest of working with Gaussian vector. So it's the corollary 0.3.1, okay? The way that is numbered, okay? Chapter 0, third section, the first of the corollary, okay? Possible. Okay. If x1, x2, so a vector with two components. If I suppose it to be a Gaussian vector, I can say the following. So I will introduce a notation that is in the beginning of the lecture's note, okay? I will write this way from now on for x1 and x2 are independent. It's a kind of orthogonality here, okay? But it means for random variable x1 and x2 independent. So if x1 and x2 are independent, what can you say about the covariance? 0. Okay? So I know in Greek generality that when I have independence and when the random variables are in L2, meaning that I can define the covariance is 0. Okay? And in general, the converse is false. But not in the case of Gaussian vector. In the case of Gaussian vectors, what is very interesting is that I have an equivalence. So to prove that the coordinates of a Gaussian vector are independent, it is sufficient to prove that the covariance is equal to 0. Okay, so something that is not interesting. Okay. So let's do the proof of this corollary. So of course I will do only one side, because this one is always true. Okay? It's this one that we are going to prove. Okay, the proof of this side, the equivalence. Okay? On met le masque? Je suis désolé. Ah, je sais, mais ça fait que moi parler avec le masque, c'est une horreur absolue. T'es allergique au masque? Je vous donne un certificat médical d'allergie. Par contre, peut-être en mettre en tissu. Oui, le problème, c'est que colle un peu, donc on peut pas comme ça. Si tu attends de moi que je te dise que c'est pas chiant, je ne peux pas te dire ça, c'est horrible. The rules are the rules. Okay? Also for the teachers. C'est une horreur. Surtout en plus dans cette salle, on ne peut pas y aller. But the first statement of this course will be no mask, no course. Okay? For the student and for the teacher. Okay, so let's call it capital X here. Okay. So I want to prove that two random variables are independent. Okay? What can I use? If I have in mind the previous proposition. In the previous proposition, I have something concerning the characteristic function of Gaussian vectors. So I know explicitly what is the characteristic function of Gaussian vectors. Is there a link between independence and characteristic function? Or moment generating function?
Yes, it depends. If we use the
Okay. So it's exactly the idea. So if I want to prove that two random variables are independent, okay, and if I know their characteristic function, it is sufficient to prove that the characteristic function of the pair is equal to the product of the characteristic function of each component. Okay? So here typically, since we have the previous proposition, we are going to use this. We have the characteristic function of the pair. Let's compute it using the previous proposition and see if I can recover the product of the characteristic function of each component, and it will be yes. Okay, so from the previous proposition, if I want to compute the characteristic function of the pair, so it's something that depends on two numbers, two variables, okay? Because here I have something that is in r to the power n with n equal to 2 here, okay? And what is this? But I use the proposition 0.3.1 and I obtain what? So I obtain exponential of I of what? The scalar product between this one and the vector of the expectations. So I obtain here x1 expectation of x1 plus x2 expectation of x2. Okay, I have this plus what? x1 x2 transpose multiplied by the variance covariance matrix multiplied by x1 x2. Okay, so I can write it this way: x1 x2 the variance covariance matrix, okay, x1 x2 over 2. I just use, okay, proposition 0.3.1. And what I have here, I have the variance covariance matrix, that is the matrix with here variance of x1, that is the covariance between x1 and x1, variance of x2, that is the covariance between x2 and x2. And what are the covariances? 0 from my hypothesis. Okay? So I have here 0 and 0. Okay? If I develop, I obtain exactly what I want. So if I develop this one, okay, I have a matrix that is diagonal. Okay, if I multiply by x1, x2, and here with the line x1, x2 and the corresponding column here, I obtain simply. So I continue my computation here. Exponential I x1 expectation of x1 plus I x2 expectation of x2 plus what? Plus x1 square variance of x1 over 2 plus x2 square variance of x2 over 2. And I see that I can separate, I have a part in x1 and a part in x2. Okay? And I remark that this is equal to what? To the characteristic function of x1 at the point x1, because I know that x1 is a Gaussian random variable with mean expectation of x1 and variance var of x1, okay? Multiplied by phi of x2. And it's close to the proof. I have proved that the characteristic function of the pair at the point x1, x2 is equal to the product of the characteristic function of each component, something that implies, in fact, that is equivalent to independence. Okay? So here, when I want to prove the independence, okay, it seems natural to deal with this one because I have the preceding proposition, the previous proposition. Okay? So I repeat that I compute the characteristic function of the pair. Okay, I use the fact that my variance covariance matrix is diagonal because the covariance is 0, that these terms are 0. I develop, and then I obtain the product of the characteristic function of each component. Okay? It's really a powerful result, and in fact, it's why we have introduced the notion of Gaussian vectors. Something where independence and covariance 0 are strongly related. Okay? Questions? Okay, so let's continue. The same idea, okay, we are going to do this little exercise here. We have 4:30, we have started. Okay, so we have finished at 4:30. Let's do the break at in half an hour. Okay. Exercise 0.3.1. So just a remark, okay? I do a video, so if c'est vraiment urgent, oui, vraiment urgent.
Oui.
D'accord, ouais, après vous êtes grand garçon, généralement il y a un break à 6 heures, essayez de...
Ok, je vais en faire un.
D'accord. Okay, so we have a break at 6. Okay, so take all your precautions, okay, not to go out. Okay. Because if I do a film, okay, of the course, if I have everybody that's it goes, okay, it will be very complicated. Okay. Exercise 0.3.1. Okay. So I consider the following Gaussian vector. I have z, that's in fact the first component, x1 xn, b, the Gaussian vector. Okay? I said the following. Write it this way. Z, that is the first component, is independent of the other components, this way, of the vector x1 xn. Okay? Z is independent of the vector x1 xn if and only if I have the following for all I belonging to 1 and xi and z are independent. So once again, it's a deep result here. So remove the hypothesis for the moment. One side is always true here. Which one? Two sides. This one or this one? This one? The right one. One of you is okay. So the good one is this one. The one that is okay without hypothesis is this one. What is the meaning for a random variable to be independent with a vector? Okay. Z independent of x1, xn means that z is independent of any function depending on x1, x2, xn. It is a very strong definition to be independent with a vector. Okay, so I repeat, z is independent of x1, x2, xn if and only if z is independent of any mappings or any random variable of the form capital F of x1, x2, xn. So in particular, it implies that I have this. Because if I am independent with a vector, I am independent with all of its components. The converse is false in general. You can be independent of all the components, okay? To be independent with the vector is something that is stronger than simply to be independent with the component. Okay? Because you have in general some relation between the components, okay? But it works in the case of a Gaussian vector. Okay, so if I know that z x1 xn is a Gaussian vector, to prove that the first component is independent of the vector, it's equivalent to prove that I am independent with each component. So something that is simpler and simpler to prove. Okay? So once again, what we are going to use, well, I have independence, I have Gaussian vectors, so we are going to deal with the previous proposition, that is, I know the characteristic function of a Gaussian vector. Okay? We are going to work with this one. So maybe I can give you want to try to do by yourself? 5 minutes? Okay, so I repeat. So the proof of the exercise. One side is always true, this one. Okay, I want you to prove this one. So you know that you are independent with each component. I want you to prove that you are independent with the vector. Okay? So I will let you try to do this by yourself, okay, but I will give you an indication just, okay? So what we are going to do, once again, we are going to use characteristic function. Okay? So if I denote this one by x, okay, the vector x1 xn by x, we are going to compute the following. So I consider t a real number and x some vector of r to the power n. This way. In order to prove that z and x are independent, we are going to prove once again that the characteristic function of the pair is equal to the product of the characteristic function of each component. So we are going to be interested in phi of, let's say, z x at the point tx. So try to compute this one, and I want you, in fact, to prove. I want you to prove that this is equal to this. Something that will give us the independence. So, okay, try to compute this one in order to prove this. And my hypothesis will be that xi and z are independent. So, in particular, that the covariance between z and xi is 0. Okay? So, 2 minutes in order to do. Try to do it by yourself. So you take a paper, you take a pen, okay, you try to do it by yourself. Okay? And the same for the student at home. Try to do by yourself. If you have some question, I can ask afterwards.
So is it similar to what we did here? Is it similar or that's a different thing?
Similar, it's not very far, but it's not exactly the same, okay? But the previous corollary tells us that if I have a Gaussian vector with two components, in order to prove that the components are independent, it is sufficient to prove that covariance is equal to 0. Here, same spirit, that in general, if I want to prove that C is independent of a vector, I have to do more than only to prove that I am independent of the component. But in the case of a Gaussian vector, it works. Okay? So something that is really strong, because to prove this independence, okay, in general, you will have to compute simply that covariance are 0 between two, okay, in order to have this. Okay? We will see that we are going to use this exercise 2 or 3 times in the course. So in general, okay, the exercise that are in the course will be used somewhere. Okay? Maybe not now, maybe in 2 months, okay, but it will be used. Question?
No, it's just.
Okay.
Oui, je pense qu'on peut les faire comme ça. Et si on utilise ce coureur-là,
C'est quoi ton exemple? Le gros?
ouais, c'est vrai que c'est le tout. Et vu que ça s'écrit comme ça, ça va comme ça, parce qu'on fait la couleur, c'est linéaire à droite.
Il faut quand même l'écrire, je suis d'accord, il faut quand même l'écrire. Hein. Là, c'est un peu short.
Oui, non, mais je l'ai pas rédigé, mais.
C'est en train de voir rédiger. Mais oui, il est à peu près là.
Mais c'est pas.
Non, c'est à peu près là. Tu peux voir quand je vais l'écrire moi, c'est 3 lignes de plus, mais 3 lignes qu'il faut mettre.
Oui, non, je l'ai pas rédigé, je suis d'accord.
Je t'enjoins à t'entraîner à rédiger. I repeat that you have everything. You have the proposition 0.3.1 that gives you what will be this term. Exactly. Okay? Use this proposition to develop the first term and see that I have some simplifications. And the simplifications will come from the fact that all these covariants will be 0. Just one remark, so for the French students, if you don't want to ask questions in English, you can ask them in French. I will try to answer in English, okay, in order to make everybody understand, but okay, so I am flexible on this point. And for the final exam, you will be able to do it in French. Okay? C'est une sorte de généralisation au cas où on a plus que deux, en fait.
Ah, ok, d'accord.
Et quand j'en ai que deux, dire que x1 et x2 sont indépendants, c'est juste l'indépendance de la valeur. Ou si j'en ai plus que deux, donc je suis indépendant d'un vecteur, je suis indépendant d'un vecteur. So someone has an idea? So I repeat, first, you just use proposition 0.3.1. You have the, what is the form of the characteristic function of a Gaussian vector. The Gaussian vector is this one, Zx, okay, the one. I know that it is a Gaussian vector for my hypothesis. So I imagine that if you have some problem, it's just a problem with notation, the way to write, in fact. Okay, more than. So, if I write it this way, are you okay? So I can say that from the proposition 0.3.1, okay, I have what? So I have the first part, that is the part dealing with the means. So it's exponential I, okay? I have what? So in the proposition 0.3.1, it's the scalar product between the argument of the characteristic function and the vector of the means. Let's do the same, okay? Write it this way. It's Tx, okay, scalar with what? Expectation of z, expectation of x. This way, if I write the expectation of x, the vector of expectation of x1, x2, xn, okay? So it's the first part, and then I have what? I have minus Tx transpose. I have here, so the matrix, okay, and I have Tx over 2. And what is the matrix? The matrix is the variance covariance matrix of, in fact, this vector here. Okay? So what is the variance covariance matrix of this vector? First, here I have the variances. Okay? And here I have the variance of the first component. That is the variance of z here. In the first term of the matrix. The first diagonal term. What are the other terms here and here? 0, because it's the covariance between z and x1, the covariance between z and x2, the covariance between z and xn, and I know that they are independent. Okay, so here, on the first line, except for the first term, I have here after 0. Here, here. And what I have here, after I have just the covariance matrix of x, that I can call this way, sigma of x, the covariance matrix of the vector capital X, that is covariance of x1, x2, covariance of x1, x1, covariance of x1, x2, and so on. Okay? So if I continue, so I erase the right part of the board, okay, in order to continue my computation here. Okay, so I can separate this scalar product in two parts. Okay.
When you write Tx in x,
So for me, yes. So for me, Tx is this one.
Okay.
Okay, I say that I take as a convention to take a vector as a column. Okay? So it's this one. Meaning that Tx transpose is exactly the same, that is just the line. Tx1, xn. Okay? So, if I continue my computation here, exponential I t expectation of z, that is this term here, the scalar product between this one, plus I x the expectation of x. Okay, it's what I obtain when I develop this one. Okay, I develop this one. For the other term, what I have? I see that in fact, when I will have t only from this term here, because all the others are 0 here. So it means that the value t will be present in my expansion only through the variance of z. Okay, so I obtain here minus t squared variance of z over 2. It's what I obtain when I do the product here, taking the first component of each vector. And I have the remaining ones, okay, that are just what happens if I erase the t, if I erase the variance here, and if I erase the t. And so I obtain minus x transpose sigma of x, x over 2. In other words, what I obtain, once again from proposition 0.3.1, I obtain here the characteristic function of z at the point t, that is this term here and here, and the other ones that give me the characteristic function of x at the point small x. What I have proved at the end is that the characteristic function of zx is equal to the product of the characteristic function, and so that z and x are independent. Okay? And you see that it is a consequence of two things. First, the fact that from proposition 0.3.1 I am able to write this formula, and then from the fact that I have an hypothesis that is z and the xi are independent, so all these terms are 0 here, and I can develop my things. Okay? So if my computation here and here are not that natural, okay, try to do it at home, okay? You will see that here is the shorter way in order to write this. You can develop with double sums if you want and so on, okay, but here you have just a compact form. Question?
I don't understand why you need to develop the expression, because you could just say that z is independent from the linear combination of xi.
Yeah?
So you have the expression of the characteristic function.
I know what you mean. Yeah, in fact. Okay, why not?
So it's what I'm
Yeah, I just have a look if you are okay or not. Yeah, I know what you mean. So where it changed something? So its idea is the following. It's just, okay, maybe another way to do, but I think that it's completely equivalent. So I take your reasoning, okay? So, please. So the idea is just to say that, so in fact I come back to the definition of this one, okay? That is, it's another way to do, okay? So, you tell me this one, maybe it's shorter to do, that's right. So in fact, when you explained to me, I didn't understand what you mean really. I think that you say this one and you don't want to do the computer, it's okay. So maybe. So what is this? I take the definition, okay? So I take the definition and I said what? I have this. So you tell me the following. So I am not sure that you have this in mind, but I will tell you the way I see it, okay? So you have this, okay? You have this. The idea is to use my previous corollary instead of proposition 0.3.1. This idea is to say, okay, instead of using the proposition in order to develop, I can just say the following. I can say that X, capital X, is a Gaussian vector. It's very easy to see this because I know that z and x is a Gaussian vector. So if I take linear combination of this one, I have just linear combination of z, x1, x2, xn. Okay? If I want to prove them to be equivalent, I know it's not enough. It's not enough. So I am agreed that you have this. It's very easy to prove that z and this one, okay, are independent. You just have to compute the covariance, for example. The covariance is 0, and from the fact that I have a Gaussian vector, okay, I know that they are independent. And so I can use this. Okay, it works. Right. So I continue. This one is Gaussian. The covariance between z and x, capital X, is 0. Very easy. You have just to compute it. What you call, okay, in fact, the fact that I have something that is here linear in each component, so the covariance is bilinear, so I can use a classical formula to do this. From the previous corollary, I deduce that since I have a Gaussian vector here and covariance 0, I have Z that is independent of X, capital X. And now I use this one in this expression to prove exactly what I want. So I am agree with you that you have here something that is, okay, what I have written here, it's not an X here, something like this, I can write it this way. Okay, it's better to do like you do. More elegant. Yeah. See. Okay, so you have here an I, you have here an I. Okay, and it works. Thank you. So it's another way, and I agree with you that it's a better way to do it. But you have to use the previous corollary. Okay, here. I use here the corollary 0.3.1. If I know the corollary, let's use it because I have proved it and it's better to do this way. If I don't know the corollary, I do the proof again in some sense, okay? I do twice. But you're right. Thank you. So less computation here, but the price to pay in order to do less computation is to use the corollary, okay, of course. So let's write it a better proof, okay? This way, okay? So by write it in details, okay, I just mean that write this also, okay? If you write it perfect. Okay, so I have this. So I keep in mind that when I have a Gaussian vectors, if I want to prove that the first component is independent with the remaining components, all of them, as a vector, it is sufficient for me to prove that the first component is independent with the second, the first with the third, and so on. So something that is easier and easier to do. Okay? So, break. Another exercise. Okay. Exercise 0.3. Okay. So I consider capital J is a vector J1 Gn, okay. That is a vector of IID and 0, 1. I remind you that IID means that independent and identically distributed. So meaning that all the components are independent, they have the same distribution. The distribution is classical and 0, 1. With Gaussian random variable, which means 0 and variance 1. Okay? Okay. I consider M belonging to R. Go ahead, okay. Vector with 10 components. And I consider A. We'll call this one M R. What is this one? Okay, it's from linear algebra. It's the set of the matrix, the square matrix of size n with real coefficients. Okay? Square matrix of size n. Okay? So I have a vector of IID and 0, 1, okay? I have a vector of real numbers and a square matrix. The question is the following. show that, and I will introduce the notation this way, okay, the notation that I don't have introduced previously. So m plus a times j. So what I have here? What is this one? M plus a times j. I have a vector here, and I multiply a matrix size n, square matrix of size n, by a vector with n components. Okay, so you have here a random vector with n components. Okay, you have a random vector with n components here. Okay, the sum of a constant and the product of something that is with constant coefficient, and j that is my vector of random variable. So I have a random vector of size n here, and I want you to prove that this random vector is in fact what? Is a Gaussian vector, okay, with a mean that is known and the variance covariance matrix that is known also, okay? So n, okay, so here I have used this notation for real Gaussian random variable, where I put two numbers here, the first one being the mean and the second one the variance. I can use exactly the same notation for Gaussian vectors. I will put here the mean vector and here the variance covariance matrix, okay? So here my mean vector is small m, vector with n coordinates, okay? And the variance covariance matrix is given by A times A transpose, okay? So show that m plus A times j follows a Gaussian vector with a mean vector equal to m and a variance covariance matrix given by this one. In particular, here you have something that is symmetric, okay? Something that we may expect from the variance covariance matrix, okay? And I will see after, when we have proved this one, okay, we are going to see how this lemma may be interesting if I want to generate a Gaussian vector with a computer. Okay? I want to generate the realization of a Gaussian vector using a computer.
It's not a Gaussian vector.
So, J of course is a Gaussian vector. Why it's a Gaussian vector? It's a Gaussian vector because you have Gaussian that are independent. But here you have inside independent and identically distributed. Okay? So you have J Gaussian vector, and if I want, in other words, what is the meaning of this exercise? It says that if I do a linear transform of a Gaussian vector, it remains a Gaussian vector with known characteristics. Okay? Okay. So I denote this one by, I will give it a name, capital Y. Okay? When I say 10 minutes, it's 10, huh? Okay, yeah. Or no more break in the next session. So what is the idea you want to use to do this?
We can just verify the definition.
Just verify, yes.
No, I mean, we do the dot product with an element.
Yeah.
We verify that it's Gaussian random variable in R.
Yeah.
And we can compute the mean and the covariance metric.
If you want. Okay. Equivalently, I can also compute the characteristic function that gives rise exactly to the same thing, because in fact I compute exactly what you say. Okay, but just writing the characteristic function. So let's compute the characteristic function of y at a point x belonging to r to the power n. Y is a random vector of size n. So when I compute its characteristic function, it is at a point that is, okay, a vector of r to the power n. So what is this? It's the expectation, okay, of what? Of exponential I scalar product between x and y. Okay? So what can I do now? I can replace y by its definition. I have a particular definition for y. That is to be this term here. Okay? I'll write it this way. It's the expectation of what? So let's do it in 2 steps. I have this one. Okay, I just replace capital Y by its definition. Okay. So I continue here. I can use the linearity of the scalar product with respect to the second component. I have something that is bilinear. And I write that I have expectation of exponential I x n plus I x a j. Okay? A j. Okay? I just use the bilinearity of the scalar product. Okay, I am linear in the second component. Okay? So what can I do? Here I have a number. It's not a random variable, this one. Okay, so using the linearity of the expectation, I can remove it from the expectation. Okay, because I have no random variable inside, it's just a number. So I can write it. This one, multiply by the expectation of what? Exponential I x a times j. So I have this. For the moment, I have simply used the definition of y. I don't have used the fact that I know something about j. I have a strong hypothesis about j. I know that it is a Gaussian vector, but I have more than this. I have components that are independent following n01. Okay? So it means that from my statement, I know this one. Phi j at the point z is known because you have n independent and 0,1. So what is this one? So I can use my proposition 0.3.1. What is my mean vector here? The mean vector, the vector of expectations here. It's they are n01, so each expectation is equal to 0. Okay, so if I compute the characteristic function, it's exponential of I, the scalar products between z and the vector of mean. So I have a 0 here plus what? Z transpose the variance covariance matrix times z over 2. What is the variance covariance matrix in this case here? It's the identity. I have 0 everywhere except on the diagonal where I have 1. Okay? So if you come back to what I have proved in proposition 0.3.1, okay, I have to do z transpose multiplied by the variance covariance matrix multiplied by z, knowing that the variance covariance matrix is equal to identity. So I have z transpose z over 2, minus, excuse me, here. Minus. Because, okay, the mean vector of j is equal to 0, and the variance covariance matrix of j is equal to the identity in size n. Okay? So I know this from the statement. So I want to use it. Okay? And I know by definition that this one is equal to the expectation of exponential I z j. It's what I know from the statement. Here it's not exactly what I have, because I have j here, okay? But but I have A before. So, do you remind how to pass this A from this place to this one? The transpose, it's exactly the definition. Why the transpose is defined, okay? This is equal to exponential I xm, expectation of exponential I A transpose xj. It's just a little of linear algebra, okay? When I have a scalar product, and if I multiply one side by a matrix, if I want to remove it and put it here, it's exactly the definition of the transpose that allows to obtain this. And now I'm happy because I have just to use this one. What will be my z? My z will just be this one here. So I just plug my z given by this one in this expression here, and I will obtain what I want. So I continue my computation. Exponential I is m. And now I use what I have written in the square here. I have exponential, okay, minus, so z transpose, the transpose of this one is what? It's x transpose, a transpose transpose, that is equal to a. This is the term here, z transpose. Identity multiplied by z, that is a transpose x. It's finished. Why it's finished? Because from proposition 0.3.1, I can say that the characteristic function of y is given by this term here. So excuse me, I have forgotten here over 2. Okay, there is another 2 here. Okay, so from proposition 0.3.1, y follows is a Gaussian vector. What is its mean? It is this mean vector. And what is the variance covariance matrix? It is what I have between x transpose and x, and this is A transpose. So I have done a little mistake, so it means that where I have done my mistake, somewhere, because okay, I want this here, and I have the other one. So let's see where I have my mistakes. Okay. So this one is okay. I just have a look on my statement to be sure that it's not me that I have. So it's A type A transpose. Okay. So a priori, what I have written here is what I have written in the lectures note. Okay. So let's see what happens. So here, problem. Here, no problem. Here, no problem. Here, no problem. Okay. So maybe I have a problem here that is here. Okay. And a priori, no. Oh, but yes, it's just, everything is okay. It's just that when I have copied this line here, okay, I have made these strings. So it's okay. No problem. Okay. So it's exactly what I want. Right?
You can calculate the expected and the variance directly for y?
Yeah. Yeah, you have formula, huh? Okay, if you know a little bit of linear algebra and relation with expectation and variance, I am agreed that you can compute. So you have to say two things. So it's exactly what your friend said just before. You can say directly that this is a Gaussian vector. Why? Because in fact it's a linear transform of a Gaussian vector, so it is a Gaussian vector. Because in the definition of a Gaussian vector, what is the definition? Linear combination of the component is Gaussian. But if you take a linear combination of linear combination, you are still a linear combination. So I repeat, linear combination of Gaussian vector is still a Gaussian vector. And I am agree with you that once I know this, I have simply to compute the expectation of this one and the variance. By linearity of the expectation, I find very simply 0. For the variance, I remove the constant because the property of the variance, and I have just to compute the variance of A times J, and I obtain this one. If you know the algebraic relation between expectation, okay, and variance by linear transform, of course you can use it. Huh? But here, if I know nothing, okay, I just use basically what I have proved previously, and I obtain this one. But I am agreed that it's shorter if you know this. Okay. It's the way to see again and again, okay, the definition of this definition. Okay. Okay, so just a remark. So if you don't have questions, so ask me if you have questions. Okay. Question? So what may be the interest of such result in practice? Let's say in real life, in fact. Okay.
I moved this. I moved this table.
You don't have to.
Okay.
Because for the other student, okay, they will think that you have an earthquake. Okay. If you want to, we can do special effect if you want. Okay. Tell me if you do this.
Okay.
Okay. So are you okay with the proof? I can erase the proof. Okay. So repeat, just compute the characteristic function from my statement and from what I know from proposition 0.3. And an application of this exercise. So as we are going to see later, and as you probably already know, okay, in finance, if you want to compute the price of derivatives, let's say, okay, in general, this price is given by an expectation. So you have an expectation to compute. So you have several situations. The nicest one, okay, is when you are able to compute explicitly the expectation. But in general, it's not the case. Okay. In the case of Black-Scholes, for example, in the case of a call option, you can do. Okay, but it's a very, very particular case. We will see later on. So in general, you have to approximate expectation. Okay? So what is the result in probability theory that I remind in the very beginning of the lecture note, before what I have done today? What is a result that allow you to approximate an expectation by something? Ben, tu dis en français.
C'est une suite de vecteurs.
Alors c'est quoi le...
de variables aléatoires.
Ouais. Et c'est quoi le théorème que tu as en tête du coup? Le théorème central unit, c'est plutôt celui d'avant, c'est la loi forte des grands nombres. So by the strong law of large number, okay, you say that, I remind it here, if you have a sequence of random variables, okay, this way, that are independent and identically distributed, and also in L1, meaning that the expectation is finite, okay? But you know, this is the strong law of large number, that x1 plus xn over n converges to have the expectation of each of them, okay? In some senses, that is almost surely or in L1. If you are not okay with all these things, okay, come back to the beginning of the lecture's notes, and you have everything that is explained. So this is the strong law of large number. The strong law of large number, that is a nice theoretical result that has some applications in practice, that is how to approximate an expectation from an average, in fact, from a mean. Okay? But of course, if I want to use this one in practice, I have to be able to compute this one. And so, with a computer, to be able to generate an independent realization of x1 with a computer. Okay? So it's what we call Monte Carlo meters. Okay? The way to approximate an expectation by a mean, okay? Generating, okay, realization of independent random variables. So that's why to be able to generate in practice independent random variables is something that is very important. Okay? So you have, it will be the objective of the course in itself, okay, that you have several possibilities to do this, okay? Do you remind how to generate Gaussian random variable? Ah, yeah. You can, but you can. In general, it's not the way we use, okay? So what you have in mind is what we call the inversion method. That is to say, okay, if I know the inverse of the distribution function, if I apply it to a uniform random variable, I have exactly the initial distribution. But unfortunately, in the case of a Gaussian, I don't know the inverse of the distribution function. I don't know it explicitly. I have a very good approximation of it, okay, but I don't have it explicitly. So it is?
I think we have formulas. It's the Box-Miller method.
You remind?
What's the name of it?
Box-Miller. So in general, okay, I don't know if you know it with these names, okay?
Is it what is?
So you have uniform distribution. So it's the way you have explicit formula in order to obtain from two independent uniform on the interval 0, 1 to independent n0, 1. Someone has the lecture's note here? You have it inside, okay? So I don't have the beginning of the lecture's note, so I have cosinus and sinus inside, okay? So I don't know exactly, so you are going to tell me. It's at the very beginning, okay? You have it here. Okay. So you consider U1 and U2, okay? Two independent. Independent uniform on the interval 0, 1. And with a computer, okay, you have a tool in general that we call the random function that do exactly this. Okay, you call the random function and you obtain randomly a number between 0 and 1. If you repeat, okay, this function, you obtain, okay, independent realization of a uniform on the interval 0, 1. So it's something that you are able to know in practice very basically, okay? If I consider G1, that is the square root of minus 2 times the logarithm, there is a pi, no, this one, so minus 2 times the logarithm of U1, cosinus of 2 pi U2, this one, okay, and I take G2, that is the same thing at the beginning, and sinus Q2. And if I have this, I can prove. And in general, it's a little exercise you do in Master 1, okay, when you see the formula of change of variable, okay, in dimension 2. Okay, you know that you have a formula that allows to extend what you are able to do as a change of variable in dimension 1, okay, but in dimension higher than 1. If you use this one, okay, you have the Jacobian inside, something like this, okay? And you can prove that G1 and G2 are two independent and 0. Okay? And it means that if with my computer I obtain very basically U1 and U2, just applying this little formula, I am able to obtain the realization of two independent n0, 1. Okay? Meaning that in order to obtain n independent n0, 1, it's very simple. I need just to have, okay, let's say n or n over 2 independent, n independent uniform on the interval 0, 1. Okay? So, by this little reminder, I said that to generate a realization of this one with the computer, it's very simple. Very, very simple, because I just have to in general to use this methodology called the Box-Muller formula that allow me, I repeat, to generate n01 from uniform on the interval 0. Okay? So it means that I am able to generate J, that is a very particular case of Gaussian vector, that is a Gaussian vector with a mean vector equal to 0 and a variance-covariance function equal to identity. Okay?
You said that if you want to generate a uniform variable.
So in general, okay, so
Like if I use it on my computer.
Random function.
Random.
But of course, what is this random function?
Yeah,
It's not that easy. Okay.
Pseudo-random.
Yes. If you are interested on this topic, but I'm not sure that you have the time now. But maybe for a project or something like this, you have on my website. Okay, just after the course of stochastic calculus. Okay, some slides that are related to a course concerning Monte Carlo methods, where I explain to you how to generate uniform. So you have methodologies that are coming from arithmetics in general. Okay, so it's not probability; it's just okay arithmetics. Then to pass from this uniform to more general distribution. So here the Gaussian, but other ones. Okay, and then how to implement in practice, okay, this kind of approximation and how to control the error you do. Okay, so the approximation rule comes from the strong law of large number, and in general, the way to control the error comes from the central limit theorem. Okay, and it's a course, that is a big course, okay, that you have, but if you are interested in, you can have a look, in particular on this one, where you have the proof of this one, okay, on the slides. Okay, it's my course concerning Monte Carlo methods in finance. Okay. But I don't need it for the moment, okay, just the little exercises that you can do dealing with the change of variable formula in dimension 2. Okay? So let's say that in a perfect world where I am able to generate this one, I am able to generate this one. Okay? So my question now is the following. Here I am able to generate with my methodology a Gaussian vector with mean vector equal to 0 and variance covariance function equal, variance covariance matrix equal to identity. Okay? What happens if I want to generate n sigma? So that is to generate a Gaussian vector with a mean vector equal to small m and a variance covariance matrix that is equal to sigma. Okay? So it's what I want to do with the computer.
I think we can use a matrix decomposition.
Yeah.
For sigma.
Exactly. So in fact, it's an application, so I need to have in mind this one. I will just explain, okay, briefly, but step one, here my sigma has a very, very particular form. That is A times A transpose. Okay, so my first step is to find A such that A times A transpose is equal to sigma. Okay? Or just a remark. Okay? So I won't enter details in order to do this. We have efficient way to do. Okay? What we call the Cholesky decomposition. Maybe if you have already seen this, but just to show you what is my problem in fact. My problem is just that I need to find the square root of a matrix, in some sense. Suppose that you don't have matrix here, but that you have numbers. I just find, okay, I want to find a square equal to, let's say, sigma, okay? And I want to solve this, find a such that a square is equal to sigma. So that is to find the square root, okay, of my number, okay? So it's an extension of finding the square root in the real number case, okay, to the case of matrix. It is possible to do, and even in any software that you are going to use in finance, you have a way to do this very efficiently. And in fact, I agree with you that we will use, okay, the decomposition of this matrix, okay, that we call the Cholesky decomposition, that allows us to obtain this, okay, in a very efficient way from an algorithmic point of view. But suppose that I am able to do, okay? So if I am able to do, it's finished in fact. Because what I have to do, if I want to generate my NM sigma, what I have to generate, I have just to do this, okay? I have to compute M plus A times J, where J follows the N0 identity of size N. I am able to do this from this. If I am able to compute this capital A, I am able to generate any kind of Gaussian vector. So just keep in mind, okay, that through this little exercise, to generate any random, Gaussian random vectors, okay, any Gaussian vector, is a priori not more complicated than to generate n independent n0, 1 through the computation of such capital A here. Okay? Is it clear what I say? So if I am able to generate independent n0, 1, I am able to generate any kind of random vector from this methodology. Okay? So, and where this kind of problem may arise in finance, so you know that in Black and Scholes, okay, so we will see later, but you have a risky asset, you want to model its trajectory, and in fact you use what? The exponential of a Gaussian, let's say. Okay, something like this. So it means that to generate my trajectory, I just have to generate Gaussian random variable using this, for example. So suppose that you don't have one asset, but you have n assets. You have a basket of assets, okay? But you can model, okay, the dynamic of these n assets, taking into account their correlations, okay, by using the exponential of Gaussian vectors in some sense, okay? And it means that if you want to generate such trajectories, you will need to generate trajectories of Gaussian vectors with particular mean vector and particular variance covariance matrix. And you will have to use this kind of methodology. Okay? But at this stage, it's just a little application of my proposition 0.2. Okay? But just to tell you that it's not just an exercise, okay, to spend the time, okay, it has some consequences in practice. When you compute, okay, the expectation of, or the price of options on baskets, for example, in the framework of multi-dimensional Black and Scholes model. Okay, at this stage, okay, questions? So don't hesitate to ask questions, it's your job. My job is to answer, your job is to ask, okay? There are no stupid questions, I say, okay? Only stupid answers. Okay, so, and even for the French student, okay? Ask them in French, not a problem. I erase everything. I will finish this part with once again a little exercise concerning Gaussian vectors. Okay, we are going to deal with the density of Gaussian vectors because for the moment I just deal with the characteristic function. Okay, just have a look on densities. It will be the way to remind the change of variable theorem in dimension n. Okay? So I keep this one on the board because I will use it. Okay. And I erase everything here, if you don't have questions. Okay. Is the end of section 0.3. Okay, it's the proposition 0.3.2. Okay? A proposition that deal with the densities of Gaussian vector when they exist. Okay? Okay. So I suppose that X is a vector in dimension n, okay? That is a Gaussian vector with a mean m and a variance covariance matrix equal to C. So X follows the n and sigma. Okay, so I have a Gaussian vector. I have two possibilities. Okay? If the determinant of sigma, so I have a square matrix, okay, so I have the right to consider its determinant, okay? If the determinant of sigma is different from 0, in fact, this Gaussian vector has a density function, okay, that is explicitly known. That is this one. I write this here. So the density function of x upon small x here, that is an element of r to the power n, and I use the definition for the density of capital X, is given by the following formula: 1 over 2 pi to the power n over 2, the determinant of sigma square root, so that's why I need the determinant of sigma to be different from 0, because I divide by it here. Okay, exponential of minus 1/2 x minus m transpose sigma minus 1 x minus m. Okay, why not? In fact, this definition is not that surprising. In particular, if I take n equal to 1, if I have a single Gaussian for n equal to 1, if I take x1 to be n m sigma square, I recover exactly what? I take n equal to 1 here and consider that I have real random variables and real numbers here, and I obtain what? 1 over the square root of 2 pi sigma square exponential minus x minus m square over 2 sigma square. It's just the analogous of this one. Okay? Because in this case, sigma minus 1 is just the inverse of the variance, okay? 1 over sigma square. And here, the number and its transform, and transpose are equal in the case of real numbers, and so I have this. So it is just the analogous of what I obtained for n equal to 1, but in the case where I have a Gaussian vector and not a single Gaussian random variable. Okay? So it's the classical quantity, okay, for the density of a Gaussian vector when, okay, the variance covariance matrix is bijective. It is the meaning of this one. Okay? Second case, if the determinant of sigma is equal to 0, okay, I say the following: there exists C1, C2, Cn belonging to R to the power n minus 0, such that what? I have this one, the sum of Ci xi from I equal to 1 to n is equal to a constant. Okay, so just have a remark on this result before to prove it, okay? So I have two possible situations. The case where my variance-covariance matrix is bijective. Okay? I can check it for square matrix this way, computing the determinant and prove that the determinant is not 0. And here, the determinant is equal to 0. Okay? What is the meaning of this one from a geometrical point of view? From a geometric point of view, what is the meaning of this? Everyone?
It's the dot product between C and X.
Yeah.
So it's the equation of an affine hyperplane.
Exactly. So if I do a picture, okay, so if I want to do a picture on the board, I take n equal to 2. I am not able to compute, okay, in the dimension higher than 2. So if I take n equal to 2, okay, I do just a little picture. So I have r squared, okay? So suppose my statement that is for two random variables x1, x2, okay? I have x1 and x2. Suppose that you are in the second situation, okay? It means that C1 x1 plus C2 x2 is equal to a constant. If I want to represent this on my little picture, what I have to draw? Where are x1 and x2? I have a linear relation here. And I said that x1 and x2, okay, so I have a line D such that x1, x2 belongs to the line. I have the equation of a line here. Y is equal to ax plus b, exactly this one with other constants and names, okay? So this is for the dimension 2, okay? If I increase, so a line is what? A line is something of dimension 1, okay, on my board that has a dimension equal to 2, okay? But here you have x1, xn, so I am now in dimension n, not in dimension 2. It belongs to the equivalent of a line, but in dimension higher than 2, that is what we call an hyperplane. 2 and affine hyperplane. What is an affine hyperplane? It's just an affine, okay, space that is just the translation of a vector space of dimension n minus 1. So it means that if I want to compute a picture in dimension 3, I know that x1, x2, x3 belongs to a plane. Okay? If I am in dimension 4, it means that x1, x2, x3 belongs to something of dimension 3, let's say. Okay? For the translation of a vector space of dimension 3. So this is the geometrical interpretation of this. I continue my remark here in this case. So I know that x1, x2 in this situation belongs to this line here. My question is the following. Is it possible for the vector x1, x2 to have a density with respect to, let's say, the Lebesgue measure on R squared? Is it possible to have this here? It will be complicated, huh? Because, okay, if I take this one, okay, in fact, I have a density with respect to the Lebesgue measure, okay, that is strictly positive. And what is the consequence of this one? It means that a Gaussian is never equal to 0. The probability is 0 with probability 0, okay, because it has a strictly positive density function. If I want to have the same in the case of this vector here, it means that since I lie only in this line, all I have here and here is 0. It means that if I had a density function, I have a density function that is only, okay, on this line with, okay, positive value only in this line. So it means that you may have sets with probability 0 or measure 0 that don't have measure 0 for the Lebesgue measure. So if you have just here, okay, you have something, okay, that belong to a set that is not the whole R squared here, but only a subset of R squared. And in this situation, it's not possible to have a density function, a strictly positive density function this way. Okay? So, when the determinant of sigma is not 0, I have a density function. When the determinant of sigma is 0, it's not possible to have a density function because I belong to something that is not the whole R to the power n, just a subset of dimension strictly less. Okay? So this is for the geometric interpretation of this. Okay? So now if I want to prove, basically. If I want to prove basically. Let's do the second part first. Okay, so I have my statement, my proposition, with the statement A, the statement B, and I want to prove there, and I start with B. Okay? Okay, so I have to find this C1, C2, Cn. And my only hypothesis is that the determinant of sigma is equal to 0. So it's just linear algebra. So how to find such a C1, C2, Cn? But I know that the determinant of sigma is equal to 0. What is the meaning of this? We are just speaking about linear algebra here. So what is the meaning of this? You have a matrix, a square matrix, with a determinant that is 0. I don't have independence. I have matrix with real numbers. Huh? Okay, so you can speak about independence in terms of vector spaces, okay, but not in terms of probability. You can say that the columns are not independent. I will do it one way to see. Okay. Meaning that the vector space generated by the columns is not dimension n, but it's not something that is easy to use in practice here. So I know that when I do linear algebra in finite dimension, the determinant is 0 means that I am not bijective. And I know that in finite dimension, bijective is equivalent to surjective, that is equivalent to injective. Okay? When I do linear algebra. Okay? In particular, if I am not injective, we can say that the kernel of sigma is not 0. I have someone in the kernel that is not 0. It is the meaning of not being injective for linear mappings. But let's take someone that is not 0 in the kernel. Let C belonging to the kernel of sigma, C different from 0. Yeah? Noyau. Le noyau, okay? It's just the set of the x belonging to R to the power n such that sigma of x is equal to 0. It's a noyau. Okay? So don't hesitate, and if you have one word in English that is not totally clear, ask the question, because I am sure that often you will know what it is, okay? You don't know the name only, okay? The kernel. So I have an element in the kernel that is not 0. Okay. So let's see belongings to the kernel of sigma not being equal to 0. So what is sigma of C? What is sigma of C? 0, because I am in the kernel. Okay? So I have sigma of C that is equal to 0. Okay? Because C is in the kernel of sigma. Okay. And don't forget that sigma is not an arbitrary matrix, it's the variance-covariance matrix of a vector. Okay? I say the following, and you are going to understand why. This implies that if sigma of C is equal to 0, I can say that C transpose sigma of C is equal to 0. Why? Because I just multiply by C transpose. Okay? But why I do this? Because we have already seen together what is the interpretation of C transpose sigma C when sigma is the variance-covariance matrix of x1, xn. It's a computation I have done at the beginning. You have here the variance of C x that is equal to 0. Because C transpose sigma C is equal to the variance of the sum of the Ci xi. Using the fact that the variance is a quadratic form. It's something I use, okay, just in the proposition 0.3.1 beginning. Okay? Okay. I say that it's finished. Why? If the variance is 0, what happens for the random variable inside?
It collapses. It's no longer a random variable.
Collapse, no. But be careful with the words. But you say that it's no more a random variable. So I mean what you, I know what you mean, but it's not exactly the good words. So a random variable that has a variance equal to 0, what is it?
It's a constant.
Constant.
Yeah.
So it is random variable, but a very basic one, taking only one possible value. Okay? If I have a random variable with a variance that is 0, it is a constant, and constant equal to its expectation, in fact. Okay? And it's finished. Because what I have here, so here it's C, you have here just the scalar product between C and X. Okay? So the C you obtain here is just the C that is an element of the kernel of sigma. Okay? And I prove this way, using an element in the kernel of sigma, that my random vector lies in an affine hyperplane. Okay? Okay. Now this one. After we go. Okay? So now I suppose that sigma is bijective. Okay? I suppose that sigma is bijective. So may I erase my proof, or do you have some question? If you have, ask them now. It's okay? Everybody? Yeah? But the question before. Question B. A remark? A question? It's okay? So I erase. So what do you want to do here?
I think we can use the distribution function in dimension.
Yeah.
And so we had
But it's what is you can yes. It's possible.
yeah, I think
No, it's possible.
I think it's possible.
Oh, it's possible. Now I just have in mind, okay, because we have to be clear when we define, okay, the distribution function of a random variable, okay. So if you have x, a real random variable, okay, the distribution function of x is the probability that x is less than small x, and I know that if this one is regular, okay, the density function of x is given by the derivative. Okay, in general, it's a way you can use in order to find the density of someone. You compute its distribution function, you compute the derivative of the distribution function, and you obtain the density function. Okay? Sometimes we do like this. My remarks is just the following: be careful because I have a less here. Okay, so it means that it's not possible to define exactly in this way the distribution function of a vector. So for a vector, in fact, what we call, so if x is a random vector, what we call the distribution function at the point small x, that is a vector, is this one. And because you have an order here, so you don't have order between vectors, you know, okay? So it's one possibility. So if you know what is the distribution function in a dimension higher than 1, you can use it, you can compute it, and can compute the derivative. So you can do, I am not sure that will be the easy way to do, but maybe, okay, you can try. It works?
Yeah.
If it works, it works. Okay. I will use another way. Another way in order to remind the chain of variable theorem, in fact. Okay? So, I have this one. Okay? And I have this one. In fact, what we are going to do is to write this one in this way. So I consider let A such that A times A transpose is equal to sigma. Okay, so it's exactly what I have done in what I have called the practical use of this exercise. Okay, let y be equal to m plus a times j, where j is equal to g1, g1, iid, and 0, 1. What I know from what I have written here, I know that y, okay, follows the n m sigma, because it is n m a transpose with a transpose that is equal to sigma. So it means that if I want to find the density function of this one, or this one, it is sufficient to find the distribution function of y. It's the same because they have the same distribution. And why it's easier to do now? Because what is y? Y is just a linear transform. A linear transform such that from this one, what can I say? If I take the determinant here, I obtain that the determinant of A square is equal to the determinant of sigma. Because you know that the determinant of a product is the product of the determinant, and the determinant of the transpose is equal to the determinant of the matrix itself. And so, my hypothesis is that here, the determinant of sigma is not 0. So, the determinant of A is not 0. And I have here this transform that is a bijective one from Rn into Rn. Okay, so if I define phi, not phi, this way, phi from R to the power n to R to the power n associated to x m plus ax, I have, okay, something that is in fact a change of variable. What is a change of variable? It is something that is bijective and of class C1, continuous with continuous derivative that is also continuous. And of course, I am linear here. Okay, so you have something that is linear. So you have a change of variable, but because of the fact that the determinant of A is not 0. If the determinant of A is equal to 0, okay, you don't have something that is bijective, okay, because you have someone in the kernel of A. Okay, but now you just have to do the job that is, okay, what I know the density of J because it's the density of a vector of n independent and 0, 1. So we'll finish here. I erase this one. We know that the density of J at the point x is what? What is the density of a vector of n independent and 0, 1? So we know that the density of the n upper is equal to the product of the density of each component. Okay, and I have n and 0, 1. So I have something that is the square root of 2 pi to the power n exponential, okay, minus 1/2 x transpose x. X transpose x being the sum of the square of the component x1 square plus x2 square plus x3 square and so on, because, I repeat, you have n independent random variable. The density of the n upper will be the product of the density of each component. What is the density of G1? 1 over the square root of 2 pi exponential minus x1 square over 2. The same for G2, the same for Gn. I have 1 over the square root of 2 pi that I multiply n times. That's why I have this one. And here I have just exponential minus x1 square over 2 times exponential minus x2 square over 2 and so on. Okay? Okay. I have everything. If you know the change of variable formula, you have the result explicitly. If not, I can do the following. So, I want to find the density of y here, because it's the distribution that interests me. So I consider the expectation of phi, let's say, of y, and I want to put it in this form. The integral over r to the power n, phi of y, okay, f of y dy. It's the definition of the density. The density is defined this way. It's the mapping that allows to express this kind of expectation using the density. Okay? So it's one way to define the density function. So I need to start from this one and to obtain something of this form here. Okay? And if I find explicitly f of capital Y, I have explicitly the density of Y. But let's do the job, okay? So what is Y? Y is this one. But I know the density of J. Okay, so I can apply the definition of the density. I can write it this way. It's the integral over r to the power n, phi m plus a times x, let's say, multiplied by what? By the density of J. The density of J, that is this one here. 1 over the square root of 2 pi to the power n exponential minus 1/2 x transpose x dx, where dx is the Lebesgue measure on r to the power n. So I have this one, and I want to obtain the previous line. What I do? I do a change of variable. I do a change of variable. Okay. Which one? I do y is equal to m plus a x. Okay? This one. In particular, keep in mind that a times a transpose is equal to sigma. Okay? And we have seen that if sigma is bijective, A is also bijective because the determinant of A squared is equal to the determinant of sigma. So what I obtain, x is equal to A minus 1 of y minus m. I am able to invert the relation. Okay, and let's apply the change of variable formula. Okay, so what is the expectation of phi m plus a j? So I start from this one and I use the change of variable formula. So it's the integral over r to the power n of what? Phi of y, because I have done the job this way. 1 over the square root of 2 pi to the power n. Exponential minus 1/2. So x is what? X is this one. Okay, so if I take the transpose of this one, I obtain what? I obtain y minus m transpose and the transpose of a minus 1. Okay, and I multiply by x, that is a minus 1 y minus 10. So my only problem is with the dx here, and you know that when you do a change of variable in dimension n, the way to pass from dx to dy, okay, is the Jacobian of the transform, okay? And here, dx is in fact equal to the determinant of a minus 1 times dy. So dx is equal to the determinant of a minus 1 dy. Because here you have the Jacobian of the transform. Okay? The Jacobian matrix of the transform, because I have a linear transform. So if I compute the matrix of the partial derivative, I obtain exactly this one. And in fact, it's more or less finished. Why? Because what I know from this one, okay, I know that sigma minus 1 is equal to what? It is equal to A transpose minus 1, A minus 1. And I know that A minus 1 transpose, I can invert between the transpose and the minus 1. I have A minus 1 transpose. Linear algebra, this. So this one is just sigma minus 1. I know also that the determinant of A square is equal to the determinant of sigma. What is the 1 over the determinant of A? This one is equal to 1 over the square root, the determinant of sigma. If you see, it's exactly what I have right now. So I repeat. In order to do the small, capital A part of the proposition, that is to find the density function of this one, I remarked that instead of using directly the definition of the Gaussian vector, I prefer to use and to come back to a transform, that is capital Y equal to small m plus A j, where j is n vector of independent and 0, 1. So I compute the density of y using this trick, the classical one, okay? So I obtain this one from the definition of y. I say that I know the density function of j because I have n independent and 0, 1. So I do this computation, and I want to pass from this form to this one. That is, I want to remove this one and make a single variable here. So I do my change of variable, this one. I have something that is bijective because A is bijective, okay? And then I apply the change of variable formula, not forgetting the Jacobian of the transform here, okay? And I see that what you obtain here, that is everything before dy here, that is exactly what I expect to obtain, is this term, that is exactly what I have. Okay? Okay, so this will be finished for today. So just a remark. So, if you see the lectures note, okay, we have done a page today. Okay? So there is a lot of things inside, huh? A lot of reminder, what is the characteristic function, okay, how to obtain density function. So, at the beginning, okay, I will go slowly because, okay, I will do all the proof and in order to train with other aspects than only Gaussian vectors, okay? So, for the next session, okay, come back to the beginning of the lectures note, read them, okay, and have a look on what we have done. What we will do next week, okay, is starting with the definition of the conditional expectation, okay, because I have martingales in head for a few weeks, okay, so I need conditional expectation, okay, in its more general definition. Okay, so see you next week.